Hello, I'm Young-Yeon and I'm going to present our paper, Dopia, Online Parallelism Management for Integrated CPU-GPU Architectures. In this work, we introduce a runtime level technique to improve performance of data parallel codes on integrated architectures using some compilation support. This work is also done with Jian Park, Florian Negle, Chang-Yeon Jo, Thomas Gross, and Bernard Egger. This talk consists of mainly three parts. I'll first give you an overview of our Dopia framework, and Jian Park and Chang-Yeon Jo will provide more details about our runtime and compilation techniques and performance modeling. Let's start with an overview of Dopia. So what are integrated CPU-GPU architectures? Integrated CPU-GPU architectures refer to integrating on-chip GPUs and CPUs using shared memory for better throughput and energy efficiency. And this kind of architecture has been widely used in many desktop processors and mobile SoCs. This figure illustrates the general software stack for executing data parallel workload on such an integrated architecture. Thanks to the modern programming models like OpenCL and CUDA, we can run a data parallel workload either on the CPU or the GPU or using the both, without needing to copy data between different processing engines. In this work, our focus is to efficiently execute data parallel workloads on a runtime system. Particularly, we focus on runtime level workload partitioning to improve the throughput of an application by leveraging the power of the both CPU and GPU hardware architectures. A data parallel workload can be divided on the CPU and the GPU because a portion of the work can be executed either on the CPU and the GPU. And there are many existing workload partitioning techniques designed for integrated architectures. For example, such a partitioning can be done with some online scheduling approaches. And one recent work uses a machine learning-based model to predict the best execution mode before partitioning. For example, as shown in this figure, the approach can predict the execution mode among CPU only, GPU only, and using the both, depending on the workload characteristics. And in case if we want to execute the workload using the both CPU and the GPU, the approach can also use a prediction model to predict the workload distribution ratio between the CPU and the GPU. In this work, however, we found that existing techniques still leave some room for improvement. What we found is that for some applications, the best performance can be achieved when using a subset of available core resources from the CPU and the GPU. And this figure illustrates one of our experiments. And the heat map here shows the normalized throughput performance of one of the benchmarks in Polybench on varying resource allocations on an AMD Cavalry system. And each grid here represents a different resource allocation. For example, we can see that the optimal performance can be achieved when we use 4 CPU threads on 4 CPU cores and 256 GPU threads among all available GPU threads. When using all the hardware resources, on the other hand, the performance was about only 78% compared to the optimal point. And for data parallel applications, it has been known that shared cache or memory level contention is usually the reason of such a performance scalability bottleneck. As shown in this figure, our goal is therefore to build a runtime system to execute the data parallel workload on the best resource allocation, i.e. degree of parallelism on integrated processor architectures. And our approach raises two major research questions. First, we don't know the optimal degree of parallelism in advance. So the question is that how can we predict the optimal degree of parallelism of an application? Second, a data parallel code running on the GPU relies on a hardware scheduler. This means that the code cannot run on a specific resource allocation. Therefore, the question is that how can you make a data parallel code malleable? And in this work, when you refer to malleable code, that means that the code can run on a specific degree of parallelism. To address these questions, we have developed Dopia, an automatic degree of parallelism manager for integrated architectures. And there are three major keywords here. First, Dopia uses a code generation for achieving malleable parallel execution. Second, Dopia uses a static code analysis to help predict the optimal degree of parallelism. Finally, Dopia is an additive runtime system running on top of a vendor OpenCL runtime system. So this means that Dopia can be applied to many existing OpenCL runtimes without modifications to the pre-installed runtime systems or the application. In this slide, I'll give you an overview of the Dopia framework. Users can run Dopia by simply loading the Dopia library at runtime. Then, at the compile time of an OpenCL kernel, our compiler tool generates some malleable code. As shown in this figure, we transform the original code into malleable CPU code and malleable GPU code. Also, our compiler tool generates a feature table of the code, and the feature table mainly contains information about the memory access pattern of the code. Then the features are used for a pre-trained machine learning model to predict the optimal degree of parallelism. And at runtime, the ML model also takes information about the input size, which is also given at runtime. Once the degree of parallelism is determined, then Dopia's dynamic workload partitioning finally executes the workload on the CPU and the GPU. In the following slide, Jian Park will provide details about the compiler and runtime techniques used in Dopia.
Hello, I'm Jian Park, and from now I will introduce our compiler and runtime techniques. First, we have to modify the kernel to control the degree of parallelism. As the GPU cannot be manually controlled by a user, we modified the code so that some processing elements do not work and remain idle. Normally, on the OpenCL programming model, the processing elements of GPU execute their work items corresponding to their work IDs. The compiler of Dopia generates code that has some if-else statements. If work items have larger IDs than the certain number, which we will put as an input on runtime, they will be an empty work, so without any computations. With this generated code, we could leverage the number of executed elements. For CPU cores, we assign work groups. So initially, all cores will execute their corresponding work groups. But on Dopia, the runtime just creates a few threads instead of using all cores. Also, the compiler of Dopia does some static code analysis to extract features which will be used on machine learning model. The memory access pattern is important considering the performance. Codes in the slides represent two kernels of ATIX from Polybatch. These two kernels look similar, but their performance is very different. Kernel 1 achieves best performance when using GPU 37.5%, while kernel 2 achieves best when using GPU 100%. This difference is derived from their memory access pattern. For kernel 1, CPU accesses memory sequentially, so it gets much cache hit. On the contrary, processing units of GPU will access metrics simultaneously with stride, which will not be on the same cache line if the data size n is large. But on a kernel 2, CPU cores will access the metrics with stride, while processing elements of GPU can access them in a row. It will access less cache lines at once and affects the performance. So we tried to characterize the memory access pattern of a kernel. Our compiler extracts the number of 4 different memory operation types, and also the number of arithmetic operations, since the memory access rate will also be important. As we run applications with data partitioning, we have to decide on which processing elements the workload should be executed. Normally, it will be done statically, which means that we divide the workload into several groups for CPUs and GPU, and keep them to the units to process. So each unit can process their work. If we do like this, there could be a problem that one unit can finish earlier than others and wait for others to finish. So it is hard to find the optimal point. So instead of using static distribution, we use dynamic distribution, which means that on runtime, each unit will get more work when they are done with assigned work. When the application starts, each processing unit will try to fetch the workload. We will distribute them some portion of total workloads. And if one unit is done, it can request more and acquire it. With this method, we could avoid the problem I explained on the previous slide. In the following slides, Chang-Hyun will provide the details of our modeling and evaluation.
Hello, I'm Chang-Hyun. I'm going to present modeling and evaluation part in Dopia. So far, we have introduced variable code execution and static code analysis in Dopia. The variable code execution enables running workload in desired CPU-GPU configurations. With the static code analysis, we can extract performance-relevant features from the given code. Now we finally build data-driven performance model on top of variable code execution and static code analysis. By running workloads having different code features, we can find patterns and use the knowledge to predict future workload. Dopia deploys ML models to automatically find patterns and to quickly build performance models for multiple target architectures. The first step to build performance model is designing features relevant to the prediction target. We explored the feature design space and defined 11 performance relevant features that are divided into 3 categories. The first category is code features. These features tell us about what memory access patterns the workload has and how many arithmetic operations in the workload. The second feature is program and info features, such as what is the workload dimension, how many work items there, and how many work items are in a group. The last category is execution parameters, which telling about how much CPU and GPU resources are allocated to run the workload. These features are extracted from a workload and execution setup and encoded as a feature vector. Now we know what information should be extracted from workload. so it's time to build a dataset. The dataset should cover the feature space as much as possible to make our model smart and to predict better. We prepared about 1,200 workloads using our synthetic workload generator. The workload generator is parameterizable, so we can generate a diverse dataset using it. In addition to that, we also prepare real-world workload to evaluate our model in realistic scenarios. Then we measure execution time for 44 different CPU, GPU configurations. This is only a small subset of the entire prediction space, but in our observation, 44 configurations are enough to find near optimal configuration. Finally, we collected data on 2 architectures, so the dataset contains in total 100,000 samples. Using the collected data, Dopia trains performance prediction model using machine learning techniques set offline. Then the trained model is deployed in Dopia to serve online prediction requests. The prediction request contains a feature vector, and Dopia makes predictions on the target prediction space. Then with the prediction result, Dopia selects the best CPU, GPU configuration and run the workload. Then here is our experimental setup. We evaluated Dopia on 2 AMD and Intel architectures to see the technique is generally applicable to different setups. 4 machine learning models are deployed in Dopia for the evaluation, and we compared our approach to widely used heuristics in practice. The heuristics are using all CPU cores but no GPUs, and using all GPU cores but no CPUs, and using all available CPU and GPU cores. The 3 heuristics and Dopia are evaluated using normalized performance. And in model evaluation, we use cross-validation to avoid the model is trained with the test data. The first result is evaluation of 4 machine learning models with Dopia on the parameterizer workload. The prediction result is presented using box plot. The bottom whisker, bottom of the box, top of the box, and the top whisker are represent pips, 20 pips, 70 pips, and 90 pips of percentile separately. The thick black line and thick red line represent mean and median separately. We found tree-based model achieves the best performance. Both decision tree and random forest models achieved about 94% of performance to Oracle in Kaveri and 92% of performance to Oracle in Skylake processor. Random forest is slightly better than decision tree, but considering the overhead, decision tree is the best, and we decided to deploy decision tree as the main mode there in Dopia. The next result is comparing Dopia versus to a wider use heuristics. The decision model is deployed for the evaluation, and we found that using a single heuristic for all cases can be a good solution. All heuristics showed poor performance, and only Dopia achieves close to optimal performance. We also measure Euclidean distance error, and it shows Dopia's prediction is also close to optimal point on the 2D prediction space. Finally, we evaluate Dopia for real-world corners. Due to the complexity of real-world corners, Dopia achieves a slightly worse result than synthetic workload. However, Dopia still outperforms other heuristics. In geometry normalized performance, Dopia outperforms the best working heuristics by 16%. And please note that the model prediction overhead is also included in the bar. It is only a very small fraction of the total execution time, since model prediction is just evaluating a single decision tree. Finally, we conclude our presentation. We have presented Dopia, an automatic and fully software-based solution for workload partitioning on integrated CPU-GPU architectures. The degree of parallelism management and static code analysis enables to build accurate performance prediction model and provide a mechanism to run workloads better on integrated architectures. Dopia is evaluated on 2 AMD Intel architectures and achieved 84% of performance to Oracle with the real-world workload. Thank you for listening, and please visit our website if you have interest in our work.